What's up, sports fans? I'm going to work through Proposition 6 with you. My encouragement is that you have the text open, you have Euclid open next to you as you watch this video. I'm also going to encourage you to pause a few times because I'm going to make this video as short as I can because I already have it all written out. So it's going to take you a little bit longer. Be prepared to pause and stuff. Okay, so here we go. If we have a triangle with two congruent angles, then the triangle is isosceles. That's essentially what we're setting out to prove here. So that's our generic conclusion. Here we go. Let's make it a little bit more concrete with a picture. So let triangle ABC be drawn such that angle B is equal to angle C. So in our picture here, angle B and angle C are the same. That's given information. We weren't we didn't solve anything there. We're saying this is our initial conditions. We have a triangle with two congruent angles. Here is a triangle with two congruent angles. I'm now going to demonstrate that these are isosceles. Actually, hang on. Let me spell out what I'm trying to demonstrate with A's and B's and C's. So if angle B and angle C within triangle ABC are congruent, then my claim is that AB, this side here, is equal to or congruent to AC. They have the same length. That's the claim. That's what I'm setting out to prove. Okay, here we go. We're using a new technique here. This is called proof by contradiction. And so I'm being a little bit sassy here, but this is generally what's happening. So let's pretend I'm wrong. Let's pretend that AB does not equal AC. So pretend I'm wrong. Then AB and AC do not have the same length. That means one of them must be longer than the other. Now, which one is longer? It doesn't really matter. Let's just say AB is the longer one. So we're saying that AB... We're saying, again, assume I'm wrong here. Assume that AB is bigger than AC. Okay, fine. Then if AC is greater than AC, if AB is greater than AC, then we can construct DB on AB such that DB equals AC. Oof, okay, let's break that down. So that means there would exist some point D on AB such that this length DB is the exact same length as AC. Again, assuming that AB and AC are different lengths and that AB is bigger, that means there must be some point D such that DB, this segment here, DB, is congruent to AC. That's the claim. Okay, now what we're going to do is we're going to explore the consequences of that claim because it just might not make sense. So our next move is to join DC. So that means draw a line from D to C. Like this. And we're going to keep exploring some of these consequences. Notice there's a few things here. Notice that DB equals AC. Well, we just said that. Yes, DB equals AC. And I have that in red here. So I'm gonna put that in red. It's kind of sloppy, sorry, but I'm trying to match the colors. DB equals AC. BC equals BC. That seems like a ridiculous statement because those are obviously the same, but let's go ahead and mark it anyway. And angle ABC is equal to angle ACB. So that is ABC, A to B to C, that's this angle, is equal to ACB. That's it. Those were our initial angles. We didn't actually see anything new here. So the same thing is equal to the same thing. Our initial angles that we said were congruent at the beginning are still congruent. And then those two lines that we said are the same, they're the same. Okay, cool. Well, then triangle ABC must be equal to DBC by side angle side. Okay, I get that in this diagram, that is tricky to see. So what I've done is I redrew this, and I redrew it in such a way where I separated triangle ABC here. Let's get that all in the picture. There we go. ABC is here on this side. And DBC is here on this side. With all the same information is true. DB equals AC. DB in red equals AC in red. BC and BC, they have the same length. I marked that with the double tick marks here in black. And then these two angles being congruent, I mark that in the light blue on these pictures. So again, this DBC is this DBC that fits inside here. I separated it just to make it a little bit easier to look at because it's trickier seeing two triangles when they're all up inside each other. Okay, so now notice we have a side, an angle, and a side congruent to a side, an angle, and a side. Well, then, of course, the conclusion here, because of what Proposition 4 showed us, or what you learned in your geometry class as side, angle, side, triangle ABC equals or is congruent to triangle DBC. So this triangle equals this triangle. Cool, that seems like a reasonable conclusion. But wait, I claim that this is bananas. There's no way this can possibly be true because triangle DBC clearly fits inside of triangle ABC. So they cannot be the same size. Here's what I mean by that. Triangle DBC is this triangle right here. This triangle right here. Let's highlight. Let's bring some emphasis to this one. This triangle DBC is clearly inside of ABC. So there is no possible way that they are the same size. It just can't be true. So we've reached an absurd conclusion, a conclusion that does not make sense. So that means our initial assumption here, the pretend I'm wrong assumption, must be false. So thus, AB not being equal to AC is an incorrect assumption. Therefore, AB must equal AC. Therefore, triangle ABC is isosceles. Euclid does define what an isosceles triangle is. It's on your green sheet in the front of your notebook. Off the top of the dome right now, I don't remember which definition it is, but it's there. It's on the back side of your green sheet. So we set out to show that if we have some triangle A, B, C, where angle B and angle C within the triangle are congruent, then what must be true is that AB and AC are the same length. And then again, the technique we chose is we said, pretend I'm wrong. Pretend that this is not true, and let's see what happens. What ended up happening is we said that smaller triangle has the same exact area or is the same exact size as the big triangle. That is ludicrous. That is not possible. So with our incorrect assumption, we reached a crazy conclusion. Therefore, this assumption right here must be false. Must be false. And if this is false, well, then this statement right here must be true. And this was the goal all along. So we demonstrated that ABC must be an isosceles triangle. Proposition 6. There you go.